We're given this question of what is robotics for this meeting, and I have to say I can't really answer that. That's why I'm starting with an epistemological note. Dan is already chuckling because he knows where I'm going. I don't know what things are. I just know what things do. So I'll talk about doing robotics, not about what robotics is. But I also have to start with my conspiracy theory figure, which shows how Dan controls my entire intellectual world. So you see the arrows here. These are postdoc advisors, PhD advisors, mentors, advisors, collaborators. Nowadays, for example, I'm mentoring some of Dan's intellectual great-grandchildren in the Technion, but my students here went to work with people, either with Dan directly or with Dan's students, and that's sort of how it goes. Basically, everything I do is somehow shaped indirectly by Dan. Thank you, Dan. I pretty much owe my career to you, and this is just an example of how. So Dan already answered this question. I think people have already quoted this, so I'm wasting my time, right? Robotics is the ability to program mechanical work. That's an answer Dan stated to me many years ago, and I've seen no reason to change that. But I will talk about how I spent a lot of my time working on various bits and pieces that Dan left in my route. One of them was this templates and anchors hypothesis, which took up about 10 years of my life. It's basically what some mathematicians and physicists call phase reduction. So Dan talked about these templates and anchors in a pretty well-known paper of his, but very abstracted models all the way down to painfully detailed models. We have this relationship between models, between templates and anchors. And so finally, thanks to Matt, we wrote some book chapters that have sort of opinion pieces on what templates and anchors might actually mean in formal sense. And I will point out, Dan's paper was in '99. This is 2016. So basically 17 years to sort out this, this idea that Dan and his co-authors left in my way. There's all sorts of formal notions of what that means, but I think I'm now buying into the argument that a template is this formal monstrosity, which I won't mention, embedded in an anchor, but that has the semi-conjugacy relationship. And the very simplest example of it is phase. And I ended up being very, very fortunate to have been mentored by both Dan and John Guggenheimer during my graduate school days. So I actually had the great pleasure of talking to Dan once a week for years, and with John working on phase estimation. So I could show that cockroaches are phase oscillators, basically. So there's this big complicated thing. It's an animal, but you see it's doing a cycle in its state space. So it's basically just an oscillator. And thanks to that came what was the first paper of my scientific career, really a book chapter written with Dan, talking about how to separate out neuromechanical control architectures based on phase. We proposed these 4 architectures, showed that they can be separated out with experiments where you look at the motions of the animal, you characterize the kind of phase outcomes on a bunch of different perturbations. You could actually figure out which neuromechanical control architecture is in play. And it turns out I needed to wait to 2022 to realize how many years Dan was thinking about phase before I started doing this. I told Dan over lunch break, this is a bit disconcerting to discover. The other kind of programming that Dan and I worked on also came from this initial interaction when I was a wee grad student. Dan gave me this problem that he solved in the 90s, which is how do you take a first order system and use it as a program for a second order system. Turned out I came up with a different answer from Dan, and we ended up with this paper that we published in 2012. So here you have a feedback control. This is just a simple feedback control, but it's figuring out how to get over a really complicated obstacle using a simple feedback law. So there are no if statements there. This is just an ODE that hits the obstacle and bounces back and to the right until it eventually gets past this whole comb of cul-de-sacs and pops out and continues on its merry way to the right-hand side of the screen. And Denise, Dan's student at the time, also did this with a Rex robot. So this is not just theoretical. Dan also taught me to think about some of these really big questions. And one of those were, why the heck are animals so complicated? So this is a question that he posed to me, and I tried to come up with an answer, and it took another 5 years, was it, Dan? I think 5 years before I managed to convince you to let me write this up. And this is this conference talk and also published paper on why we need more degrees of freedom. And sort of beginning to answer this question of, is robotics is a kind of computation? What are notions of computational complexity that we have? What are fundamental bounds on the computational complexity of programming work? In this case, making stability basins that we can switch between quickly turns out to immediately force us to increase the mechanical complexity of our system for fundamental reasons. And that's the topic of that paper. But most of what I'm going to talk about today is one of the projects that started from a paper with Dan. But in that diagram of various ways in which Dan indirectly and directly influenced my life, there are a lot of cross paths in the history of this paper talking about event-selected systems. So I'll start with this. This is a YAR. This is yet another Rex robot, in this case built by Gavin when he was still a grad student, and came and helped me in my lab, and finished by George Council, who later on became a postdoc in Aaron's lab. So you see these connections there. And it's pointing out this issue. When you see this Rex walking around, simultaneous contacts are common. 3 legs are hitting the ground almost at the same time. The dynamic description is hybrid. But in general, if you have multi-contact systems like that, multiple discrete events, you can have all sorts of horrible things happen. Discontinuities, non-smoothness, non-determinism, lots of other things. Wouldn't it be nice to have a class of these systems that's tamer and easier to understand? So thanks to another trajectory in that world, here Sam Burton, who is Eric Klavan's undergrad mentee and also worked with Dan and also worked with Bob and me in Berkeley and with Shankar Sastri's student, we eventually defined this class of systems called event-selected systems in a paper that I will of course point out has Koditschek as one of the authors, because this is still Dan's influence, where we talk about systems that have multiple intersecting hybrid transitions and what happens when the system flows through what is potentially an initial condition dependent order of impacts. And so, I'm going to have these little screen caps of horrible formal stuff from the paper, and I'm going to skip through them as though they don't matter, because they don't matter. This is just about the concepts. So the idea is here we have a bunch of smooth manifolds, which are the guards, the conditions for impact, for example, and we flow through them somehow. And it turns out that there's a useful class to think of there. So there are lots of types of hybrid dynamics. If we start and we have these red and blue events that can happen, in general, everything could be completely history dependent. We have no events happened, here event 1 happened, here event 2 happened. And when 2 and then 1 happen, you have something different than when 1 and 2 happen. That's history dependence. If you have complementarity systems, the kind of systems that people think about in mechanics, often you have a system where you have a vector field. Here you add some A, here you add some B, and if you went through them, you add A plus B. So they have a lot of structure and they're much, much simpler to analyze. Event-selected systems stand in the middle. That is, what governs the event-selected system is not the order in which event happened, but just which subset of events has happened already. So it's empty set, 1 has happened, 2 has happened, 1 and 2 have happened both. The order in which 1 and 2 have happened is not important. If that's the case, you have an event selected system, and that sort of sits in the middle in terms of complexity. What we proved, thanks a lot to Dan hammering us on simplifying our proofs and arguing with us constantly that we're writing incomprehensible gobbledygook, is that there is a unique flow that arises in these systems. So these systems don't have these multiple outcomes possible. And it turns out that these flows have a kind of derivative. And again, this was a really important insight that I learned through interacting with Dan about these questions of stability in engineering, how important it is to have first order approximations for systems. So these are the things that govern stability and that control theorists care deeply about. Yeah, that's linear. And it works for a little bit. It works for a little bit. So if you don't have that, you're really in trouble. And so we managed to show that these systems have what is essentially a derivative-like object, which is not a classical derivative. It's what is called a Bouligan derivative, hence the B differentiable on this slide. And what people care about is stability, is really the variational equation. Here I will say a bit about the equations on the slide. So normally we write it this way. We look at the derivative of the trajectory, and we say it depends on the derivative of the flow, on the Jacobian of the flow. But as we saw in Aaron's presentation right before me, when you hit a hybrid transition, there's something called a saltation matrix. This sort of beast here appears and takes that first order perturbation volume and skews it. So you saw that circle of initial conditions going through the hybrid transition, becoming an elongated ellipse. That was a great example of the saltation matrix. And if you have multiple switching events, you just have multiple of these acting in some order. Unfortunately, they might not necessarily commute. And then Dan intervened again in our life, because in beginning of 2021, Pramod was awarded the Bodhi Prize, and Dan came to us and said, is there something we could do with our work that's related to what Pramod did? Because you remember this paper that he wrote with another student, Richard Groff, whose work I followed again because of Dan. This keeps closing. So I was trying to reproduce Joel Weingarten's work, who was using Richard's Groff work. So I was familiar with these ideas of piecewise linear approximations. And these piecewise linear approximations are exactly what that Bouligan derivative that we needed was. And so we quickly put together, Sam and I, this archive paper, which has a terrible, terrible implementation of this idea, but good enough for Dan to have presented at least a slide or two about it and saying, here, we're still using the work I did with Pramod. And this matured into a paper that actually just now got finally in print. So you can still find the archive, but the paper's now in print finally, that shows us how to do this. And it's really been one of the most satisfying papers to write in my career, as you'll see on the next slide. But the key insight is this: you have this complicated nonlinear system. We have nonlinear guards, nonlinear flows. But if you zoom, as we know, manifolds are just hypersurfaces. And so the manifolds become hyperplanes, and the changing vector fields become constant vector fields. And we have what we call the sampled flow. And that can be integrated very, very quickly. And when we integrate that very quickly, we get this. And this is why I'm so satisfied with this paper. So 11 lines of Python code and 30 pages of math to prove why these 11 lines are correct is to get if you spend life thinking about math the way Dan taught me. And so this enables us to take models, and I won't go into the details of this model, just say, here's a two-legged thing hopping on the ground. The legs might hit in various orders, and therefore it will have this sort of event-selected behavior. But when we use that observation, those 11 lines of Python code, this two-legged stool hitting the ground is computed 1,400 times faster. And this actually gets better and better as the complexity increases. So for a three-legged stool, we got about 43,000 times faster. So 4.5 orders of magnitude. And this is why thinking about the underlying math and physics is so important, because you could throw machine learning at this all day and you will not get an insight that will give you 4.5 orders of magnitude of improvement on your performance. You need to actually try and understand problems deeply in terms of the topology, in terms of the math, in terms of what they really mean. And that tenacious need to understand things fully is part of Dan's legacy, I think, to all of us. And so with that, I'll go to my conclusion. I don't know what robotics is, but I did learn from Dan that you need to ask the big fundamental questions and not be afraid of them, not be afraid of deep math. Sometimes you need to just lean in there and do math that hasn't been done, or talk to mathematicians and really, really get the deeper insights, and you will end up doing interesting robotics. And by the way, for those of you who care about implementations, a fast integrator using those speedups should be coming out of my lab shortly. So thank you, Dan, for all of these great insights and contributions.